Alright everybody, welcome back to another episode of Psytrance for Beginners. This is episode 2 and today we're going to look at some audio basics. Now this isn't going to be the most interesting chapter in this series. I know it's just something that I need to get through for the other chapters to make sense. Obviously I want to give you guys a strong basis before we get into the actual music making so that you actually know what is going on when we're starting to make music. So in the last episode we talked about DAWs, which is the program that you see here. Today, as you can see, we have a few tracks with some audio loaded. You can see that in this one I have audio disactivated, which I can change with a keyboard shortcut. I also have this group here, which I have set to a volume of -20 dB. And this is just a setup that I have prepared so that I can start to talk about digital audio. So the question that we have to answer first is, how does sound exist within the computer, within this DAW? What is sound in there? And really what it comes down to is that it's a series of numbers. For that to make sense, let's zoom into this audio file here. You can see if I zoom in that you can see this line here. This is the line which represents what the speaker is doing. We have two lines actually. You can see a top one which is for the left speaker and a bottom one which is for the right speaker. And the main assumption here is that we're working in stereo. If you're working in any other format, the amount of lines that you see within an audio file may change. But for 99.9% of the cases you will be working in stereo, so two lines is what you should see. Now if I zoom in more, you can see that the line starts to flatten out. Obviously we're looking at a smaller and smaller portion of the audio file. And now we get to see points. And these points are what is actually being saved within the memory or saved within the DAW while you're working on the audio. The reason why we use these points is because we cannot store everything. We don't have infinite amount of hard drive space. So we need to have some kind of interval at which we say, okay, the speaker is here now, the speaker is here in the next point, the speaker is here in the next point after that. We cannot store all of the information in between the points. So what happens is that a measurement is made here, a measurement is made there, a measurement is made there, and everything that happens in between here is just kind of filled in by virtue of having these points very, very close together. I've quickly made a selection. This selection has a length of 1 millisecond, so 1/1000th of a second. So you can imagine that because there's many of these points in 1 millisecond, there's really a small amount of time between all of the points, between all of the measurements. So between here and here is a fraction of a millisecond. So what this means is when we press play, the devices that are used for outputting the sound, the audio interfaces and the speakers, don't actually get to see this. They get to see some points. And at some point, those points need to be converted. Usually that's the job of the audio interface, but in some systems it may be the job of the speakers or the card in your motherboard or some other part as well. The important thing to realize is that at some point, these individual points that represent what the waveform is doing, what the audio is doing, is converted into actual electricity, which then becomes a wave without any of the points, a continuous wave. That is then sent to the speaker, and the speaker is actually reproducing that waveform so that you can start to hear it. This is called digital to analog conversion. And the reason for that is within the digital domain, we tend to think about sound as something that is limited within storage. So you need to use some kind of sampling technique or some kind of measurement technique to get all of those individual points. Whereas in the analog world, that works with electricity, which can have a lot of different values in very short amount of times, potentially infinite. So all you need to remember here is that this continuous wave here is actually what is being played with the speakers, but within your computer or within your DAW, it is summed together from all of these points here. This point is played first, then this next point, then this next point, then this next point. And at some point, some kind of conversion technique is used to get all of the values in between. Now with a recording, you can imagine that it's the other way around. I'm currently speaking into a microphone right here off the screen, and that microphone is hearing a continuous wave, which is my voice. It is continuously receiving pressure, which it then captures and turns into a digital signal at some points down the chain, before it actually becomes the audio file that I'll eventually use in the edit for this video. That is obviously the opposite, so there we have analog to digital conversion. Before we had digital to analog conversion, now this is analog to digital conversion. So going back to these points, I do want to say one final thing about them, and that's that these points have a very special name. They're called samples. Now you may have heard about the term samples before because it's also the term that we use for little audio files that you can drag into your projects. If you've already explored music production a little bit, you'll probably be familiar with the term sample pack. those are different samples than the individual points of an audio file. They're the same word, but used in two different ways. So here you can see this point is a sample, this point is a sample, this point is a sample, this point is a sample. Those are individual samples of this audio sample. I know it's confusing, but that's just the terms for that. The reason why these points are called a sample is because, again, of that measurement that we're doing. We're looking at the waveform and we're trying to take a sample from it. We're sampling this waveform, taking measurements to determine what the value of these points needs to be to represent the waveform that it needs to play. So when sampling, what determines the distance between these points? And why is there no point in the middle, for example? Or why is there no point here or here? And what determines what the height of these points are going to be? All of those are questions that you probably have right now. So let's try to find an answer for that. First thing that we can find is that if I activate this other audio file here, you'll see that the points line up here. This point lines up with this point, and this point lines up with this point. So they're sampled at the exact same rate. So the rate at which these points are measured here is called the sample rate. How many times per second do I take one of these samples? How many times a second do I make one of these points? So the sample rate determines the precision over time, over this length value here. But we also have the amplitude, right? The y-axis. How many different values can each of these points obtain? You can probably imagine that if the point that we have here was only limited to being a 1 or a 0, an on or an off, that you don't have a lot of information in terms of the amplitude that you're able to represent. But if I zoom in here, you can see that all of these points, there are slight differences between them so that they can follow this line. So the vertical precision, or the precision on the y-axis, is determined by something called the bit depth. And you don't really need to know where the terms comes from. It's a computer science thing, but it basically determines the precision that you have in terms of amplitude for each of the samples that you have. Now, every setup is going to have a different way of setting this, but I can set my sample rate right here, which is 48,000. So per second, we're making 48,000 measurements. And through my audio driver settings, I can also set my bit depth, which I leave at 24 bits. If you know anything about computer science, you know that 24 bits is 3 bytes, which is enough to store roughly 16.7 million different values. Now, I'm telling you all of this because it's important for what we're doing next. It's not important that you actually know what is happening within your project when you start out producing music. Whenever you open your DAW with some settings, it's usually going to be fine in terms of bit depth, in terms of sample rate and all of that stuff. You're not going to be in the position where from the get-go they give you a DAW where the settings aren't good enough in terms of quality or in terms of the individual settings that you have. I just want you to know all of this because it's going to be important in what we're going to be looking at next. And that's going to be summing. Summing comes into play when we're looking at multiple audio files. So we can see we have this track here loaded up with this waveform that's going up and down like this. And then we have this other audio file which has the same kind of waveform but faster. You can see it has the same up and down motion. It's called a sine wave, this kind of wave. It has some very nice properties which we'll look at later. But you can see that this is double the speed as this one. What will happen when we play them together is that we can look at the individual points of both of them and we can see their bit depth value for each of them. We can then sum them together. So if this one is a positive value and this one is a positive value, we get a more positive value. These two peaks, this peak and this peak, therefore, sum together into a higher peak. So what I'm going to do is I'm going to take this audio file, this one is the first one, and this audio file here, and I'm going to sum them together into one audio file by recording the output of this group. You can see both of the tracks are active, therefore they're both going to go into the group, they're going to sum together there, and then we're going to record the result of that back into this other track here. Let's look at the resulting waveform. We saw that the group was at minus 20 dB, but our audio file turns out to be at minus 14 dB, so we have summed together and we've lost about 6 dB of volume. And you'll see that this is the result of the sum between this audio file and this audio file. And hopefully you can kind of see the effect of both of them. You can see that this peak here is represented here, and obviously this one is summed together here as well. And then you can see this peak kind of sitting in here, but it's lower because this other waveform is at its lowest point. And this would also be true for 3, 4, 5, 6, 7, however many different audio sources you have playing at one single time. what is happening is that they're all summed together, and then that will become the output. But one of the things that I didn't really show is how do we sum these together, because what are these values? Well, the way that I like to think of it personally is that they are values between 1 and -1. And the reason for that will become obvious if I turn this a little bit higher. You can start to see this line appear. And this line is what represents silence. So we'll use 0 to represent the silence. Therefore, we have 1 at the top here, 0, and then -1, 0, 1, and so on and so on. And obviously, these values are sitting somewhere in between. Okay, so now that we know the basics about summing, let's look at some properties for these audio waveforms that we've been looking at so far. What you can see is that I have here a sine wave with 100 Hz and a sine wave with 200 Hz. And the reason why I know that is because I just generated them with that exact frequency. For those that don't know, a frequency is an oscillations per second. So you can think of an oscillation as starting from the middle line somewhere and then going up back to the same point. Notice how before I said that this is going twice as fast as here. That's because this is 100 Hz and this is double that in 200 Hz. So this waveform goes up and down 100 times a second, and this waveform will go up and down 200 times a second. And there's a fun thing that we can do in that we can verify that. Here I have an EQ and this has a spectrum display. This is something that can tell us the frequency of a sound. You can see all of the EQing stuff that is in here, which we'll talk about in the later part of this series, is actually turned off. Everything here, you can turn it on, but I've turned it off. We're just going to use it to look at what the sound does in terms of the frequency space. I've deactivated the 200 Hz one, so we should see a single spike here at this 100 Hz part. And that tells us that there's a sound playing at 100 Hz. But how does the PC know? How does it know what is happening? And why are there a little bit of a fall off to both sides when you get lower in volume? And why is there some clicks happening if I start and stop playing? What is happening here? Well, there's some quite complicated math that allows you to go from the time domain into the frequency domain. And what that means is, right here, we're looking at the waveform in the time domain. It just tells us what the speaker is doing over time. What is the amplitude of the speaker, or what's the position of the speaker comb as it's playing. For this waveform here, the speaker comb is going back and forth twice as fast to reproduce a sound that is higher in frequency, for example. And again, looking at it, we can also verify that it shows up on the spectrum analyzer. Notice that this spike in this case is at 200 Hz, and there's a little thing here that shows you the frequency as well as its volume. So the way that you convert between the time domain and the frequency domain is through the Fourier transform. Fourier was a French mathematician who came up with this technique to basically take different signals and decompose them into their individual frequencies. This was used a lot in physics, but it also had massive implications for us audiophiles because it allowed us to check out what the frequency of an individual sound is. Now, up until this point, we've been looking at sine waves, which have a very neat property in that they're only one frequency. I have this sine wave 100 Hz here, and it just shows up as one spike. I can take a different sound and it will show up as many spikes. To verify that, I'm quickly going to go into a sample pack that I'm working on, and I'm just going to get a random clap sound. This is a digital sounding clap, but it should do the trick. Notice that there's a lot of small spikes that are showing up here. So the Fourier transform, what it does is it takes our sound that we're just playing, whatever sound it is, if it's this clap or this sine wave or some of the other waves that we'll be looking at later, and it takes those and it turns it into a frequency domain. So what you'll get is, instead of the amplitude over time, you'll get the amplitude per frequency. But actually we're not using the actual Fourier transform, because the Fourier transform in its conception uses infinities. It only really works on signals that are infinitely long. But with the signals that we have, they're not infinitely long. They're clearly bound by some kind of time, right? In the sense that this sound that we see here, if we disregard the silence, is under 200 milliseconds long. But still we can see the frequencies that it uses. And that's because what we can essentially do is we can approximate the Fourier transform. And that's really what's happening in here. There's not a real Fourier transform, but it gets approximately close enough so that Any differences between a potential actual Fourier transform and the approximation that we're making here are so small that it's good enough for what we're dealing with. What that does mean for us is that when we're looking at the Fourier transform of, for example, a single sine wave, which remember is an individual frequency, we get these little clicks at the start and the end, and we get this tailoring off bit here and here. Again, this is amplitude per frequency. So this is really cool that we can take the time domain and turn it into the frequency domain with relative ease, in the sense that we just have to do this approximation of this very big calculation, and all of the errors that we're getting are in essence negligible. There are some edge cases which we may look at in the future, but for now we can just say that whatever we see here is a good representation of the waveform that is actually happening here. But what if we want to go back? What do we do then? Let's say that we have something happening in the frequency domain here, and then we want to go back into a time domain. Well, we can actually use the exact same calculation in reverse. You can just take your frequency domain, apply the Fourier transform, and you'll get back a time domain signal. So you'll get back an audio file. Now, obviously, again, you don't have to do that manually. The PC is doing that for you. But to go from the time domain into the frequency domain, the calculation is the same as going from the frequency domain into the time domain. So now that we know how this Fourier transform works, let's look at a different waveform. This is going to be a saw wave. And you can see, for obvious reason, why it's called a saw wave. It has the look of a saw in the sense that it goes up, and then over time it goes down again, and it snaps up, and over time it goes down again. This one is also playing at 100 Hertz, and let's have a look at what that looks like. You can see that you get that one peak at 100 Hertz, but then there's also a whole bunch of other peaks higher and higher up. The reason for that is a saw wave like this does not have one single frequency. It's actually made up of a whole bunch of different sine waves, all playing at different frequencies. Remember how I said before that Fourier found a method of taking a signal and decomposing it into its frequencies? What I really meant was that he found a method of taking a signal and decomposing it into sine waves. So a signal like this, which looks nothing like a sine wave, can be represented if you have enough different sine waves playing at different frequencies. That other factor that goes into it has to do with something called phase. And phase really is the starting position of a waveform. Now I'm quickly going to jump into a plugin because this is the best way of representing what is actually happening. Don't be scared by what you're seeing here. All we really need to look at is this phase parameter here. For now, I want to turn down the randomness so that we have this position here, which is the phase. And you can see that there's this line. This line is determining the starting position of the waveform whenever you play. So if I want the waveform to start playing from this position right here, I'll set the phase right there. If I want to start it playing from that click part where it snaps down, I will set it right here. If I want to play from the second half, I'll set it right here. And that's just called the phase. The reason for this has to again do with mathematics and the underlying way that trigonometry works. You don't really have to know why this is the case, so I'm not going to dive deep into it. It's just interesting that a lot of this is actually tied into math. And it just goes to show that music making can be very, very technical if you wanted to. Now, one of the things that I want to say at this point, and maybe I should have said it before, is that you don't really need to know all of this technical stuff. It's just going to prevent you from making weird decisions or maybe even mistakes, as some would call them, in later parts when you're actually working on music because you don't know the technical things behind it. The goal of this series is really to lay the technical foundation that you would need to just make the music that you want to make. And I promise at some point we'll get there. So for that decomposition trick into sine waves, what we actually need to know is three things. When we take a waveform like this and we want to represent it with sine waves, we need to know for each sine wave its amplitude, its frequency, and its phase. We can see two of them with this analyzer here. Unfortunately, there's not really a way to show the third one. The reason for that is because it's a determination of the starting position and all of these effects are really happening in real time. They don't really know when you start playing a sound. So there's not really a way for you to tell what the phase of a sound is if you don't know when the sound is starting to play. Even now when I'm not playing the sounds, this effect is actually still working. It's still doing work. It's just working on silence and therefore nothing is showing. But the frequencies and the amplitudes of these individual sine waves are able to show up on this analyzer whenever I press play. You can see we have a first peak here at 100 Hertz. which has a very high amplitude. And then it goes to 200 Hertz, where it's a little bit lower amplitude. Then it goes to 300 Hertz, and it has a little bit of a lower amplitude still. And that kind of goes on up until the very high frequencies here. So you may have noticed a few things already. You may have noticed a bunch of patterns, and you may have also noticed why this is called a saw wave playing at 100 Hertz. The lowest peak is what determines the frequency of a sound. And actually, if I drag this sine wave in here, you'll see that they'll have the same oscillation time. From this point up until this point is the same as from this point up until this point. So a sine wave at 100 Hz takes the same amount of time to oscillate as a saw wave at 100 Hz, or any other wave at 100 Hz. The second thing that you may have noticed is that there's this pattern where you have the lowest peak basically being the highest amplitude, and then all other peaks existing at a multiple of the frequency of the first one. So the first peak exists at 100 Hz, then all other peaks will be 200, 300, 400, 500, 600, 700, and so on and so on. And each of these individual peaks is called a harmonic. So you have the first harmonic, which is the lowest frequency, and you have the second harmonic being the double of the first harmonic. You have the third harmonic, which is triple the first harmonic in terms of frequency, and so on and so on. The lowest harmonic, or the first harmonic, is also often called the fundamental, because it determines the frequency of the whole sound. And really what differentiates the tone of each sound that you hear, even real-world instruments like a violin from a piano or a guitar, is how the different harmonics have an amplitude and phase. So each of the sine waves used to create the complex wave that you're looking at is going to have a different amplitude and a different phase. And all of that together is going to culminate in a specific type of waveform, which is going to be the sounds that you're hearing. To prove that, I've also taken another waveform, which is called the square wave. You can see why it has this square up, down kind of pattern. And this waveform is special in that all of the even harmonics have an amplitude of 0, so they're silent. And if I play this, you'll be able to see that in the spectrum analyzer. When there's this switch here, you'll see that some of the harmonics are going to drop out. One of the interesting things to note here is that because we have fewer harmonics in the sound, because all of those drop out, you can actually see that the amplitude of each individual harmonic is going up. The reason for that is overall, these waveforms have the same loudness. So these individual sine waves that make up this waveform have to be louder to get this whole thing to the same loudness as this thing. The final thing that I want to show you in today's video is one of the interesting implications for all of the things that we've been talking about so far. Let's say that I have this saw wave and I want to change its tone a little bit. What I can do is add an EQ to it, and now you can see that all of these bands are active. I've turned all of them off but one, and what this device allows me to do is it allows me to draw in a line that will be applied to the harmonics. So what will happen is the sound will come in, a Fourier transform is taken, it will be converted into the frequency domain, and then it will say, okay, we'll follow this curve, and here you can see we have a 9.38 dB boost, or whatever it is, 9.33, and whatever volume this line has will be added or subtracted to the harmonics that cross this line, right? So if you have a harmonic at 100 Hz, it will get a little bit of a boost in volume. If you have a line at 500 Hz, it will get a lot of boost in volume. Then another FFT is used to turn it back into the time domain, and it will be sent to your speakers. And you will hear that you get a different sound. If I turn this effect off, now what I'm going to do is I'm going to use some automation. So I'm going to go into automation mode, and I'm going to turn this device on halfway through playing, so that we can see the difference between not having it on and having it on. And then we'll record the result of that. Let's turn up its volume so that we can analyze this waveform. And you'll see that we have two different variations of the waveform. We have our standard saw wave, and if we go into here, we have a different waveform, which is now doing a saw wave plus this EQ boost here. Now you can see that we've kind of lost this initial click here. It has turned into this kind of wobble here. And there's a very good reason for that. If you're going into the frequency domain and then back into the time domain, and you make some kind of edit in the frequency domain, what will happen is you will not only change the amplitude, but you'll also change the phase. Remember, the phase is the starting position of each of those harmonics. And really what you're changing is the difference in phase between all of the harmonics. That's what we're interested in. We're not really interested in the absolute phase of each harmonic, but mainly the differences between them. The way that I'm going to show that is I'm going to go back into this plugin here, and I'm going to open up the window here, and this shows us these individual bins. What this is a representation of harmonics. So here we have the amplitude of each of the harmonics. Remember that the lowest harmonic is the loudest, and then we go progressively lower and lower in volume. And then these lowest ones are the phases. So here you can see we have this saw wave. This is a little bit different from the saw wave that we saw before, in that here we are ramping up, and in this one we're ramping down. So you can see this one is going down. Instead, this one is going up. But in essence, it's the same sound, just kind of flipped on its head. What happens if I change the phase of just one of them? Well, you can see we no longer have a saw wave here. We just messed up this kind of waveform here. So again, that goes to show that any waveform that you see, any wave cycle that you see, is achieved by having very specific amplitudes and very specific phases, obviously for each of the harmonics. Therefore, applying some effect that will change the amplitude of some of the harmonics relative to other harmonics will also change their phase, which is in reality what this EQ8 device here is doing. So I think that's enough learning for today. We covered a lot of different things and a lot of technical stuff, a lot of very complex stuff. Hopefully I could explain it all clear enough. If I didn't explain something clearly, then obviously feel free to leave a comment down below. This stuff has to be clear before we go into the next bit, because it's going to make all of the other things that we're going to do in the next episode and beyond much easier to understand. Now, obviously, as most things, this is something that you build an intuition for. I have a pretty clear intuition of what is happening to my sound when it goes through a certain effect. When you're a beginner, you're not going to have that intuition, but over time, when you get more and more used to what is happening, it will become clearer and clearer what is actually going on. So in the next video, I'm going to go over kick and bass. It's going to be the bread and butter of Psytrance, of making Psytrance, and it's going to involve a lot of the things that we talked about today. However, that is going to be a very long video. I haven't recorded it yet, but I already know that it's going to be a very big topic to cover, as there's a lot of things that go into it. So that may be even 2-3 hours long in terms of video length. What that does mean is that I'm going to need a lot of time to actually script that and prepare that video, so it may not come out for a while. Already this video, as you can imagine, took a long time to prepare, took a long time to get all of the examples and the exact things that I wanted to say. So if you did enjoy this video, let me know by leaving a like. And if you're new here and you want to see where this series goes, make sure that you're subscribed. Finally, another way to support the channel is by watching some more of my videos. So I'll leave a few of them in the cards. But that's going to be it. I hope you enjoyed, and I hope to see you in the next one. Bye bye.